Welcome to the second part of Module 4. Let's start by taking a look into some examples of DSS. An example of a DSS used for optimal herbicide applications is the Danish Crop Protection Online CPO, which provides information about the need for weed control and the optimal herbicide combination at the optimal rates. The herbicidal treatments as proposed from CPO are estimated according to herbicide dose-response curves, which are parameterized with experimental data from many years of herbicide testing under field conditions and data as derived from the manufacturers of the herbicides. LCIS DSS is an irrigation support system which improves the efficiency of water use in precision agriculture based on three different methodologies: IRISAT, remote sensing, WMOD, simulation modeling, and W10s, situ soil sensor. Moreover, the AgriSupport 2 system aims at adopting the latest advances in decision support systems to fulfill the needs of agricultural production processes. Riccio et al., 2003. The overall objective of this system is to provide farmers with sufficient agricultural decision-making suggestions like farm operation scheduling, detailed operation cost, resources usage, and profitability analysis. The decision-making process in AgriSupport 2 system is computed by a farm planning model algorithm. This algorithm is designed to identify which work units are suitable for performing what tasks. After obtaining necessary inputs, the farm planning model algorithm computes the cost of all feasible modes and compares them with each other in order to find out the one with the lowest cost as the optimal plan for distributing agricultural tasks to work units. This algorithm adopts the Cplex optimizer as the decision-making tool. The Smart Irrigation Decision Support System, SIDSS, as its name suggests, helps irrigation activities to achieve better performances with the minimum water usages. The reasoning process adopts two machine learning techniques: partial least squares regression, PLSR, and adaptive neurofuzzy inference systems, ANFIS. PLSR is used to deduct unnecessary variables when soil measurements and meteorological data appear redundant. ANFIS is employed to minimizing estimated errors under a given threshold. The output of SIDSS presents the optimal irrigation plan, indicating the amount of water usages and the time for irrigation activities. Moreover, Fuzzy Decision Support System, FDSS, is an improvement over an existing irrigation web service based on IRINET model, and Middle Rio Grande Conservancy District, MRGCD DSS, helps to analyze water demands in service areas and schedule available water resources to fulfill these demands precisely and efficiently. Case studies and implementation. Successful examples of DSS in agriculture. 1. Crop Protection Online, Weeds, CPO Weeds. Crop Protection Online, Weeds, CPO Weeds, is a decision support system for weed control developed in Denmark and later adjusted to conditions in several other countries. In Denmark, the DSS includes all major crops and available herbicides. The background for developing CPO Weeds was a political motivation for reducing pesticide use and the concept of factor-adjusted doses. It was never the intention to build a sophisticated scientific model, but rather to design a simple, user-friendly system. It is a knowledge-driven DSS, which offers herbicide dose suggestions based on a large database of the existing knowledge of herbicides and herbicide efficacies. Several names for the system have been used in the English literature, including PC Plant Protection, Denmark, Plant Protection Online, Denmark, VIPS Ugra, Norway, CPO Weeds, Spain, and DSS Herbicide, Poland, Germany. Second, AgroIT/AgroDSS. A case study was performed on data that were obtained from one of the partners, Slovenia, that collaborated within the EU-funded project, AgroIT. The goals of the AgroIT project were to implement a cloud platform for integration of existing applications for farming and to facilitate the pilot use of those applications. As a part of the AgroIT, 4 pilot projects were initiated in 4 EU countries, including the TrapView 4 platform that was implemented by EFOS. The farmers and analysts from the AgroIT project team reported that the use of AgroDSS brought a significant added value to TrapView users. Although TrapView already contained its own decision support module that is based on monitoring, it was not able to make predictions. For the future, AgroDSS supplemented the basic decision support with predictive functionalities that enabled farmers to effectively plan spraying according to the predicted population size of particular pest species. 3. Olive cultivation in Andalusia. In southern Spain, olive growing is an important part of the economy, especially in the provinces of Jaén, Córdoba, and Granada. This case study included the first stages of an Information and Decision Support System, IDSS, for providing different types of users, farmers, agricultural engineers, public services, etc., with information on olive growing and the environment, and also assisting in decision-making. The study processed uncertain or imprecise data, such as those concerning the environment or crops, and combined user data with other scientific experimental data. The possibility of storing agricultural and ecological information in fuzzy relational databases, vital to the development of an IDSS, is described. The information was processed using knowledge extraction tools, fuzzy data mining, that allowed rules on expert knowledge for assessing suitability of land to be developed and making thematic maps with the aid of geographic information systems. Flexible querying allows the users to collect information interactively from databases, while user information is constantly added. Flexible querying of databases, land suitability, and thematic maps were used to help in decision-making. Integration with AI and precision agriculture. In the current technology-based era, the concept of big data has emerged, which is the bulk collection of various data including soil architecture, weather forecast, climate change, fertilizer recommendation, disease management, and crop mapping. These data are extracted by means of several resources like Internet of Things IoT system software and web portals for useful information. This information is also generated by big data that is implemented by robots and some forms of artificial intelligence, AI. A transition is noticed in society, and people have moved from agricultural culture to cities to get good urban facilities, which caused workforce shortage. One solution to facilitate this shortage of workers is agricultural robots integrating AI features. According to a Forbes study, farm robots supplement the human labor workforce and can harvest crops at a higher capacity and faster pace than human-based agronomy. Although there are numerous cases in which robots are not as compatible as humans, agriculture industries are currently developing robotic systems to work in the field and help producers with tedious tasks. The introduction of robots in agriculture drastically increased productivity in several countries and reduced the farm operating costs. Also, robotic applications in agriculture are growing exponentially. Robotic applications offers promising solutions for smart farming, like handling labor shortage and a long-time declining profitability. We have come to the end of this module. Thank you for staying till the end.